For energy-saving reasons, in new, low-energy buildings, ventilation is not achieved anymore by simply opening the windows. Instead, centralized ventilation systems provide clean, fresh air to the interior spaces. These type of systems use the warm outgoing air to heat up the cold incoming air and therefore allow comfortable as well as energy efficient living. The ventilating fans and the heat exchanger are usually located in the basement of the building and require a widely ramified air duct system. This obviously makes these kinds of systems problematical for installation in existing building stock. Although there are already some compact devices for retrofit installation on the market, they have only limited efficiency. The aim of the project Vent4Reno was to develop a compact, decentralized ventilation system with high efficient heat recovery for the minimal invasive refurbishment of existing buildings. The key concept to make the system compact yet high efficient was to combine the ventilating fans and the heat exchanger in just one component.
The characteristic property of this so-called counterflow heat recovery fan is that only one crossflow fan generates both airflows at the same time, and the fan blades work as regenerative heat exchangers simultaneously. Both airflows and the fans through the blades symmetrically, but at different levels, perform a level change inside the fan and are blown out again through the fan blades. Through this flow conduction, it's possible to realize a counterflow regime to achieve a highly efficient heat recovery, and in addition, occurring condensate can be recovered during the cold and dry season and no frost protection is required.
Based on the results of the numeric simulation, we designed a 3D model for the development of a prototype. The aim here was to design the device as compact as possible, but at the same time fitting all the relevant mechatronic components in it. For the production of the prototype, we used 3D printing techniques which allowed us to realize affordably the complex geometries of the device, especially of the heat recovery fan with its numerous thin blades. Through its sensors and actuators, the device is able to measure the indoor air quality, namely the CO2 level, the temperature and humidity, as well as differential air pressure, and therefore allowing automatic control strategies like demand-based ventilation and airflow balancing.
The prototype was installed and tested in the climatic chamber, where different climatic and weather conditions can be simulated by changing the outdoor and indoor temperature and humidity parameters.
With this prototype, we were not just able to develop a compact, decentralized ventilation system for the retrofit installation in the existing building stock, but we were also able to demonstrate that these kind of devices can have a high efficient heat recovery by making aerodynamical and thermodynamical changes to existing concepts. In Europe, the building sector accounts for 40% of the total energy consumption and approximately 36% of the entire CO2 emissions. In addition, given the low building turnover rates, transforming the existing building stock into high performance can have a huge impact on making our world more sustainable and climate friendly. And we believe that these type of devices can and will certainly play a key role.